Okay, so trying to find the Maclaurin series for this would be tough. The derivatives are going to be really yucky and gross. Instead, what you can do is find a Maclaurin series for something really similar. So let's do g of x equals the cubed root of x plus 1. Because if we can find a Maclaurin series here, we could even call this y if you want. We'll substitute 2x to the fifth into wherever our x is in this Maclaurin series. So this one's a lot easier to deal with because there's no 2 times anything in the denominator that's causing the chain rule to happen over and over again. So following the steps of the Maclaurin series, the first step is no derivative. Plug in your center. It's Maclaurin, so it's 0. And then 0 factorial times x to the 0. So if I plug in 0 in here, I get out 1. 1 divided by 0 factorial is 1. X to the 0 is 1. So this is all just 1 for the first term. The second term relies on the derivative. So the derivative, the 1/3 comes down. It gets reduced by 1. So 1/3 minus 1 makes negative 2/3. So if I plug in 0 into the first derivative, that gives us 1/3. And then I need to divide it by 1 factorial. So that's times 1. And now that's x to the first power. And the next step is the second derivative. So negative 2/9 x plus 1 to the negative 5/3 because we took a derivative. So if you plug in 0 in here, you're going to get out negative 2/9. And now you're going to divide it by 2 factorial. Don't forget that part. So 2 factorial is 2. And this is x squared. And then the third derivative, the negative 5/3 comes down. So that's 10 over 27. It's x plus 1, the negative 8/3. So if you plug in 0 in there, you're going to get 10 out of 27 times 3 factorial. 3 times 2 times 1 is 6. Okay, so we got a Maclaurin series for something that looks really similar. We can make a Maclaurin series for this, and then we can just integrate term by term. So the Maclaurin series we want is going to be 1 plus, we're substituting 2x to the fifth everywhere where we see an x. So this is 2x to the fifth over 3. Subtract. This is, those will cancel. This is x squared over 9. And then this is here 5 and 3. Is that 27? Yeah, so 27 times 3, that's, oops, what was I doing for? 27 times 3, so that's 5 over 81, x to the third. Okay, they wanted the integral, though, of f of x, so you just have to integrate term by term. Because the integral operator is a linear operator. If you integrate this entire thing, you can just integrate term by term, just like the derivative operator. So the integral here is x. The integral here, it's going to be x to the 6, so I'm going to do 2 over 3 times 6, x to the 6, because you multiply by the reciprocal of the new power when you find an integral. Oh, I'm sorry. Here, when I was substituting, this should be 2x to the 5th that I'm plugging in everywhere, right? 2x to the 5th squared. This should be 2x to the 5th to the third. Very sorry about that. So this is actually 4x to the 10th because the power on top of power multiplies. So it's 4x to the 10th over 9. And then to integrate that, it's going to be x to the 11th. So I want to divide the whole thing by 11. And we said 2 squared is 4. So very sorry about that mistake. So same thing here. This term is actually 5 over 81. And then that should be 2 to the third, 2 to 8, x to the 15th. And so when we integrate this, it's going to be x to the 16th. And we need to divide it by 81 times that 16 because we found an antiderivative and still have a 5 in the numerator. Okay, there's the first 4 terms. I think that's what they're looking for. We just need to simplify the fractions if necessary.